All right, let's review, do your review sheet. Remember, this is due before you take the test. Now, the primary formula you're going to use is 1 over F is 1 over SO plus 1 over SI. And in general, you're going to be solving for the image distance. Now, you can do this a couple of ways. You can, if the numbers are reasonable, you can just solve 1 over SI is 1 over F minus 1 over SO. And then you can find the least common denominator and of F and SO, do your subtraction, and then remember to flip your answer. Now, sometimes you're not going to have nice, neat numbers. So at this point right here, what you're going to do is find the least common denominator symbolically without your numbers. So that's, oops, 1 over SI. 1 over SI is, it'll be FSO divided by SO minus F. And then flip your answer. SI is FSO divided by SO minus F. Then plug your numbers in. When you do this, multiply F times SO first. And then do the subtraction. All right, so you'll get a number divided by another number. Then do your division. Otherwise, you can get some really weird answers. Now, list in order of increasing frequency the waves through the EM spectrum. Well, I have them here. Radio, microwave, infrared, visible, UV, X-ray, and gamma. Remember, radios have very long wavelengths, very short, very small frequencies, while gamma rays have very short wavelengths, but very large frequencies. And as you go up, this relationship, V equals F lambda. Oh, sorry about that. Let me erase that. I don't even want to use V, do I? Let me use C. These all travel at the speed of light in a vacuum is equal to F lambda. So these two have to equal the answer down here, number 3. The speed of light in a vacuum is 3 times 10 to the 8th meters per second. Now, what is an EM wave? Borrow this from your Hewitt textbook. It is a wave that is partly electric, partly magnetic, carries energy. It's emitted by vibrating charges. As you move away from the source of a light, what happens to the brightness? Well, it decreases by 1 over r squared. So if this is my light source and I'm some distance r away from it, and it has some level of brightness at this point right here, when I'm at another r, so when I'm out here at 2r, the brightness is 1 over 2 squared, or 1/4. Now, to do diffuse versus specular reflections, I borrowed this image from the physics classroom, and it's an excellent source of information on physics if you want to go there. A specular reflection is a smooth surface, while a diffuse is a rough surface. So parallel rays will come in and bounce off nice, even and parallel on a specular reflection. Now, of course, these are mirrors. Well, a diffuse reflection, they'll come in and it's rough, so they're going to bounce off in all sorts of different directions. So let's see, your paper is specular. What else? Your shoes are specular, the floor. It's not been polished very well. What's the law of reflection? It's the angle of incidence equals the angle of reflection. Remember, we always measure with respect to the normal. So if this is my surface, my normal is this perpendicular line. We're going to pretend like that's perpendicular. This is the normal. It's a perpendicular line. So if I have a ray coming in at some theta I, it will reflect off at theta r. Now, when you look at a plain flat mirror, what's the image like? Well, it's always the same. The object distance is always the same as the image distance. And the height of the image is always the same thing as the height of the object. What are the differences between concave and convex mirrors? Well, convex has a negative focus and concave has a positive focus. Okay, a concave will look like something like this, while a convex will look something like this with my object on this side. Now, a concave is always going to give you a virtual, upright, reduced image. While a concave, well, it might be virtual, it might be real, it might be upright, it might be inverted. It could be real, or actually it could be virtual as well. Or you know what? You might have no image. All of this is for concave. Now, which one is the only one that can produce an enlarged image? Of course, that's concave. All right, if a person stands 48 centimeters in front of a concave mirror with focal length of 20, where does the image appear? All right, so SO is 48 centimeters, and it's concave, so the focus is positive, so F is plus 20 centimeters. So 1 over F is 1 over SO plus 1 over SI. So I don't want to do least common denominator with these, so I'll do it this way. I'll do it with my symbols. And I'm going to get a least common denominator with my symbols. That's FSO is SO minus F. Now I'm going to flip it. Now I want to plug my numbers in. The focus is 20 times 48 divided by 48 minus 20. Now go ahead and do your multiplication and your addition, etc. right now. So 20 times 48 is 960. Where's my pen? There we go. Come on, pen. 960. And 48 minus 20 is, of course, 28. Now 960 divided by 28 is 34. 0.3, that's close enough, centimeters. Magnification is minus SI over SO. So it's minus SI, which is positive 34.3, divided by SO, which is 48, which is negative 0.71. Now, because my magnification is negative, I know it's inverted. Because my magnification is less than 1, I know it's reduced. Because my image distance is positive, I know it's real. Now draw the ray diagram. All right. Whoa, that wasn't very good. Let's do that one again. You're going to do these, and you're going to use a ruler. I don't really have one. So here's my mirror. And remember, you always kind of put in the back of your mirror. And let's call this 20 my focus. So this is my center of curvature. So this is 40. And so my object will be about right here. All right, your first ray, you go in parallel. Remember, that's always parallel to this principal axis. And it's going to bounce off through the focus. Make sure you put your arrows. Second ray is into the focus. And then you bounce off parallel. You see, you can always see where they're meeting. But we're going to want to put in our third ray, which is through the center and back on itself. Now look at that, they all intersected. That doesn't usually happen on mine when I freehand them. All right, so this is where the image is. Start on the principal axis, drop down. Now if a person standing 4 meters from a convex mirror, convex means focus is going to be negative. So my object is 4 meters, and my focus is negative 6 meters. Where does the image appear? Now, when I did this, apparently, I did it for a concave mirror. So your answers are up here incorrect for number 11. Just happens. Sorry. 1 over F is 1 over SO plus 1 over SI. So 1 over SI is 1 over F minus 1 over SO. Now this one's simple enough. I'm going to put the numbers in. So this is 1 over negative 6 minus 1 over 4. Now let's see. My common denominator between 4 and 6 is 12. So this would be 2, 2. So I'm multiplying by 2 over 2. Here I'm multiplying by 3 over 3. Now be careful with your algebra here. So this is negative 2 minus 3 divided by 12 is 1 over SI. So this is negative 5 over 12. So SI is negative 12 divided by 5. 12 divided by 5 is, I believe, 2.4. So where's my pen? Negative 2.4. Now because it's negative, I know my answer is virtual. Let me go into magnification. Magnification is minus SI over SO. So it's minus negative 2.4 divided by, what was my object, 4? So negative times negative gives me a positive. So it's going to be positive. 2.4 divided by 4 is 0.6. Now, because my magnification is positive, I know it's upright. Where's my upright? And I've got the magnification. Because the magnification is less than 1, I know it's reduced. Now let's do a diagram. All right. There's a 6 centimeter focal length. So here's my focus, and here's my center. Now it's 4 meters, so it would be about right here. All right. Remember, always go from the back of your mirror. Now your first ray is in parallel, and then it's going to bounce off as if it comes from this focus. Remember, we only dot back the reflected rays. The second ray is in through the focus, but then it's going to bounce off parallel. So it's going to go in like it's going through this focus, so line up your ruler. It's going to go like this, but it's going to bounce off parallel. And we see these aren't going to intersect, so I'm going to go and dot these back. And the last one is straight through the center, which is right there. So once you hit the mirror, you start doing dotted lines. All right. So there's my image. That's where these three intersect. Now we see, indeed, we have a reduced virtual upright image. Now, if a light ray hits a mirror at 25 degrees, what's the angle of reflection? Well, 25 degrees. What is the index of refraction? Index of refraction is defined to be the speed of light divided by the speed of light in that medium. So this is speed of light in a vacuum, and this is in the material. What happens to light at the boundary of two transparent mediums which produce different indexes of refraction? Well, say this is my normal, this is my boundary. And say this has N1 and this has N2. A light ray is going to come in and it's going to bend either toward or away from the normal. So the answer is it's going to bend. When light leaves glass at an angle of incidence 20 degrees and enters air, is the angle of refraction greater or less than 20? All right. I'm going to show you exactly how I figure these out every time. All right. Think of air. And remember, N of air is equal to V1, and N of water is 1.33. All right. Here's my normal. All right. Light comes in, and I always draw it at 45. That's kind of 45. All right. It always bends toward the normal for water. So, remember, light is reversible. So if it leaves glass, which would be down here, at 20 degrees, if this is 20 degrees, so let's say N of glass is, I don't know, 1.5. That's actually a reasonable one. If this is 20 degrees, this is clearly going to be more than 20. So it's going to be greater. All right. When going from less dense material to more dense, okay, when going from less dense to more dense, it bends toward normal. When going from more dense to less dense, it goes away from normal. Now up here, the speed, this is also a faster, and this one is slower speed. The garden gnome is 0.2 meters from a converging lens. So now we're doing lenses with a focal length of 0.18. Where's the image? Okay, so SO is 0.02 meters, and it's converging, so the focus is going to be a positive 0.018 meters. Where's the image? 1 over F is 1 over SO plus 1 over SI. So 1 over SI is 1 over F minus 1 over SO. Now these aren't very pretty, so I'm not going to try and find a least common denominator with them. So I'm just going to do the least common denominator with the symbols. So now I'm going to flip it. SI is F SO divided by SO minus F. Now remember, all this practicing we've been doing in class with this was really going to pay off here. So F is 0.018. SO is 0.02. SO is 0.02 minus 0.018. Now be careful with your calculators. Okay, 0.018 times 0.02 is 3.6 times 10 to the negative 4. So let's just do this. 1, 2, 3, 3, 6. We'll do it that way. And 0.02 divided by minus 0.018 is 0.002. All right. When I do this, 0, 0, I get, my answer is 0.18 meters. What's the magnification? Magnification is minus SI over SO. So it's minus 0.18 divided by 0.02. So 0.18 divided by 0.02 is 9. So let's see. The magnification is negative, so it's inverted. The magnification is greater than 1, so it is magnified, enlarged. SI is positive, so it's real. Now we're going to do this diagram. We'll go back to black. All right. Now it's a converging lens. You remember converging lenses are a little fat in the center. Let's make it fat like that. Now, the whole point here for this diagram, it's 0.2 meters and the focal length is 0.18 meters. So if this is my focal length, my object is going to be just slightly outside of my focus. And we always go from the center. All right, so I have focus over here, focus over here. All right, principal rays. In parallel, it's converging, so they're going to, parallel rays are going to converge. All right. Now, in through the focus, out parallel. And then the last one is straight through the center. So here's my image. It's where these 3 rays cross. Put an arrow, bring her down. Now, if the wavelength of light, lambda, is 1 times 10 to the 2 meters, what's the frequency? Well, it seems like I didn't give you enough information, but you know the speed of light is 3 times 10 to the 8th meters per second. You know c is f lambda. The frequency is c over lambda. Now you plug your numbers in. 3 times 10 to the 8th divided by 1 times 10 to the 2 gives me 3 times 10 to the 6 hertz. If the index of refraction of a transparent medium, N, is 1.32, what's the speed of light in the medium? All right, well, I know the speed of light in a vacuum is 3 times 10 to the 8th meters per second. And I know the index of refraction is defined to be C divided by V. So I want to find V, so I'm going to get rid of my denominator, so I'm going to multiply V. So NV is, those are canceled, C. So I want V, so I'm going to divide both sides through by N. So V is C over N. Now I plug in my numbers. 3 times 10 to the 8th divided by 1.32 gives me 3 times 10 to the 8th divided by 1.32 is 2.27 times 10 to the 8th meters per second. If light traveling from air enters a transparent medium with an index of refraction of 1.23, so we've got this situation right here. This is N of air. I know N of air is 1, and N of my medium is 1.23, and it enters it at an angle of 30 degrees. All right, so this is 30. All right, I'm just doing the diagram. You don't have to do it. Theta R. Okay, N of air is 1. Theta of air is 30 degrees. Index of your material is 1.23, and we're looking for theta. All right, you're going to use Snell's law. N1 sine theta 1 equals N2 sine theta 2. All right, N of air is 1 sine 30 equals 1.23 sine theta 2. All right, don't panic here. Let's go on and find out what the sine of 30 is. Put 30 in your calculator and then hit your sine button. All right, sine of 30 is 0.5. It's 1.23 times the sine of theta 2. Now let's divide both sides through by 1.23. So sine of theta 2 is 0.5 divided by 1.23. And just find out what that number is. I'm going to stick it in my calculator here real quick. I get 0.40650465. Okay, there's 065. All right, these don't actually matter. So what this is saying is the sine of this angle is that number. So I want the angle. So what you need to put in your calculator is inverse sine. So I'm going to apply inverse sine of this thing. All right, so I'm hitting inverse sine and then 0.40650465. And I'm getting an angle of 23. 23.9. Let's just go with 24. All right, good luck on them.